Solution dilution kind of rhymes. In the lab, in the stockroom, we often store solutions in a more concentrated form, and we refer to these as stock solutions. We stock them in the stockroom, right? And for some of the same reasons that they sell orange juice in concentrated form, it's more convenient. When we use these stock solutions, we need to dilute them, just like when you buy the concentrated orange juice in the little can and you want to drink it, you don't just drink it straight out of the can, right? Because it's too strong. You dilute it. How do you dilute orange juice? You add water. So when we dilute a stock solution, we add more solvent. Usually it's water, but other things can be solvents as well. And there's a relationship between the concentrations and the volumes of the dilute solution and the concentrated solution. And that is this dilution equation, which looks a lot like Boyle's law, doesn't it? Boyle's law was P1V1. This is M1V1. So M1 and V1 are the molarity and the volume of one solution. M2 and V2 are the molarity and volume of the other solution. And it doesn't matter which one you call the more concentrated and which one you call dilute. This works because the moles of solute in each of these solutions is the same. Let's think about that. Molarity has units of moles per liter. So if we take the molarity of one solution times its volume in liters, what unit do we end up with? Moles. So the left side of this equation equals the moles of solute. Think about the orange juice. You've got this can, it's got orange goodness in it, right? And you pour that in a pitcher, and then you use that cup, that can, and you put 3 cans of water in. Do you have more orange goodness in the pitcher than you did in the can? The amount of orange stuff is the same, right? It's not more, it's not less, you've just added water to it. The volume, the concentration, molarity times the volume equals the mole of solute. The mole of solute in the dilute solution is equal to the moles of solute in the concentrated solution. The concentrations are different, the volumes are different. So that's why this equation works. This equation applies only to diluting solutions. Do not use it with stoichiometry. It's tempting, and what's especially dangerous is that sometimes it'll give you the right answer. If all the coefficients are 1, it'll work beautifully. But that's not always the case, so don't even go there once. And don't use it for titrations either. Just a lab safety notice. When we're diluting acids, we always add the acid, the concentrated acid, to the water, never the other way around. So I'll tell you a story. At a different community college in this area, several years ago, a student worker was working in the stockroom and making a diluted sulfuric acid solution from concentrated sulfuric acid. And he forgot this important point. And he had a large graduated cylinder, I think one of those 4-liter ones, big cylinder of concentrated acid. And he added the water to the acid. When you dilute an acid, it generates a lot of heat. And when you add the water to the acid, it can generate so much heat that it can cause the acid to boil. Have you seen what happens with the test tubes when you get them too hot? They start to boil and come up, and you can see how they could shoot out, right? This is like a cannon of sulfuric acid. It got so hot it was boiling, and it shot concentrated sulfuric acid straight up, and it was dripping off the ceiling and running down the walls, went all over the place. They had to call the fire department and the police, and the hazmat team had to come in, and they had to file incident reports with OSHA and it made the news, and it was just a big deal. Thankfully, the student worker was wearing his safety glasses and his lab coat, and he did get some mild chemical burns, but he did recover fully. If he had not been wearing his safety glasses, it would have been a very different story. So that's an example. It's a little too close to home. Always add the acid to the water. And one thing that helps me remember that is, a lot of people around here have swimming pools, and sometimes you have to add acid to the swimming pool, right? So you've got this acid, which is kind of concentrated. It's not super concentrated, but it's pretty concentrated. You're adding that to this big swimming pool of water. That's the correct direction. You don't want to add water to the more concentrated acid. So let's do a calculation. How much 6 molar sodium nitrate solution should you use to make 0.585 liters of a 1.2 molar sodium nitrate solution? Well, let's look at this question. Here we have a concentration of sodium nitrate. Here we have a volume and a different concentration still of sodium nitrate. Those are the clues that you have a dilution problem. You're going to have 2 molarities, or 2 volumes, and the compound is the same. So we've got, we'll call this one solution. They're asking how much. We want to know the volume of that one. And then we've got this one. Do you see how this volume and this number of moles are together in the problem? This volume of that, those go together. You can call them 1 or 2, I don't care, but those are both the same solution. So let's call this volume 1 and molarity 1. So V1 equals 0.585 liters, and molarity 1 equals 1.2 moles per liter. Oh, we need a 1. That would make this other solution, solution 2. So molarity 2 would be the 6.0 moles per liter. And volume 2 is what we're trying to find. This is one way to approach this problem. I did it a little differently this morning, and if you want to see that one, you can find the YouTube video and watch that. So what's the equation? M what? M1 V1 equals M2 V2.
How do you know that 0.585 is the first volume and then?
Well, I know that the question is, how did I know this was the first volume? I could call that the first volume or the second volume.
Okay.
It doesn't matter. What matters is that I couple this one with this one. Those have to go together. You can call them 1 or 2, doesn't matter, as long as you pair them up correctly. So that's our equation, and we're trying to find V2. So then this equation is nice, it doesn't have a fraction in it. So we're just going to divide. We'll divide by M2 on that side to get rid of it, and we'll divide by M2 on this side. So now we have volume 2 is equal to, molarity 1 is 1.2 moles per liter times volume 1. Did I say molarity 2? I don't know what I said. It's molarity 1, whatever I said earlier. 0.585 liters. And that's all divided by the other molarity, which is 6.0 moles per liter. Now, one of our favorite things is to give you a problem like this and then mess up the units, mess around with the units. Stick them in and see if they cancel out. If they cancel out, it's fine. If this volume was in milliliters, that would be okay. We don't have to convert to liters. It's just then volume 2 would be expressed in milliliters. But here we see that moles per liter cancels moles per liter. And we're left with a unit of liter, and that's nice because we're supposed to be calculating a volume. So we have 1.2 times 0.585 divided by 6. How many sig figs should this answer have? 2. 0.12, and the unit is liter. Any questions? Solving this problem is the same as solving a Boyle's law problem with volume and pressure of gases. Mathematically, it's exactly the same. How do we make a dilute solution? Well, you figure out how much you need. So here, we're trying to make 5 liters of a 1.50 molar KCl solution from a 12 molar stock solution. So 5 liters and 1.5 molar go together. And 12 is the other one. So here we've got, see, I don't like it when they do this, but here they did it anyway. What on earth did they do? Oh, they solved it and then they stuck the numbers in. Yeah, forget that. Anyway. You'd solve the problem just like we solved the previous one. That's just confusing. It's confusing to me. You solve it and you find you need 0.625 liters of that 12 molar solution. So you're going to take that stock solution, the amount that you need, and you're going to put it in the flask. This is going to be a 5-liter flask because that's the volume we want to have. Now, they show putting it into an empty flask, and this is potassium chloride solution. It's not an acid. So probably there's not going to be any issue. But personally, I would put some water in there first and then add the concentrated solution and then swirl it around, mix it up, and then dilute it to this final line.